So let's continue our discussion about thermodynamics, and I want to talk about different types of thermodynamic systems. The first one is a closed system, and a closed system is simply defined as a system where we have no material moving across the boundaries. So if I just draw myself a little box and I put water in it, and I don't allow any water to come out of the box, this is a closed system. Now the thing about a system like this, we definitely can have energy transferred across the boundaries, but we don't have any materials crossing the boundaries. So I might have some heat going into our system. So I might have some, if I go ahead and have some flame here outside, some hot heat source, and that heat source may transfer some energy through the walls of this container. Let's just say this is some sort of metal container here. This water is in a metal container. And this heat outside from this fire can transfer through the walls of this container into the water inside. We've seen this oftentimes when you're cooking. So if we go ahead and make ourselves a little pot here, and we put a lid on it, and we put some water inside, and then we go ahead and put it on your stove. If we put it on the stove and we get a little heat here, what will happen is, the water will essentially, if it's a tight lid, the water will stay inside here. If this is tight, then there's no water that can escape or steam. But what will happen is the burning unit or heating unit on your stove will heat up the bottom of the pot, the bottom of your pot here, and that bottom of the pot will get hot, which will in turn heat up the water, and eventually it'll start to boil. And again, if this is tight lid, then it's a closed system. And that's essentially what a closed system is, where we do not have any boundaries or anything moving across the boundaries. Let me just draw one other type of closed system that we may encounter, and this is where we may have movable boundary system. So we can imagine we have here in some sort of a piston where we have some space in here that I've drawn here where we have air. And then at the top of this space we have some part that's able to move up and down. So this can move up or it can move down. And it can move up and down depending on the volume of the air inside. Now the air can never escape because this is a closed system, but the volume of this air can change depending on the temperature and the pressure and so forth. And this is still an example of a closed system. It just involves changing volume. So in the next system we want to talk about are open systems. So here's an example of an open system where we have some material flowing in and we have some material flowing out. So it's open because the material can leave and enter, but we also might have some energy transfer. For instance, I may have some heat that I'm heating within this part right here. I may heat inside here, and so that the fluid, in this case, whether it's water or whatnot, it might have a higher temperature coming out than it went in. And this is just an example of an open system that we may have to deal with. And in fact, actually, most of our systems will be open systems because a lot of times we're dealing with flowing materials. But this is, again, the other type is an open system. So let's talk about the different types of energy. So every material has energy within that material. Every material has energy built into it. So every chemical we deal with has some energy, and we call this energy the internal energy. It's the inherent energy of a material. Oftentimes this will be written as U. U, if you ever see U in the context of thermodynamics, that means internal energy. And the reason why molecules or atoms or different chemicals have energy is a variety of reasons. One is translational, or that's the energy of motion. So molecules and atoms are always moving around. Show you here, they're just kind of, if we had a gas, we would see atoms moving constantly, and there's some energy associated with that motion. There's vibrational energy. So in this case, this is a diatomic molecule, or in other words, it has two atoms, and this molecule is vibrating. There's almost like a little spring here between these two atoms, and this bond distance is changing constantly as it vibrates. There can also be rotational energy. So this molecule here may be rotating around, and there's energy associated with those rotations. And finally, there's chemical energy. So chemical energy is the energy associated with bonds. It's the energy associated with nuclei. This is the energy inherent in a molecule. And it takes energy to break bonds. If I want to take this bond right here between these two atoms and break it, it requires energy. There's some strength or energy that's inherent in these bonds, and that's part of the internal energy. So all these different types of energies combine to make what's known as the internal energy. Every different material has a different internal energy. So for instance, water will have a different internal energy than carbon dioxide. Carbon dioxide will have a different internal energy than, say, sulfur. And that internal energy, again, depends on the material. The other thing we need to realize about internal energy, it depends on the state of the material. So if I have water at 25 degrees Celsius and 1 bar, that is different than it will have a different internal energy than at, say, 300 degrees Celsius and 1 bar. So the temperature and the pressure determine the internal energy of a system. Or we can also derive the internal energy based on the pressure or volume and temperature. And the reason is because these are not independent. Once I've established what the temperature and pressure is for a system, I now have defined the state of that system. And we'll talk more about that later, but the short end is that the short explanation is that the state of a system, meaning the temperature, the pressure, the volume, etc., that determines what the internal energy is of a system besides what the actual chemical is. Let's talk about enthalpy. Enthalpy is probably a concept you haven't dealt with before, or maybe you touched on it lightly in some of your chemistry courses, but enthalpy is defined as U plus pressure times the volume. And this is just the internal energy plus this PV term. And so PV is approximately the energy it takes to flow a system. So when we are dealing with flowing systems, we will deal with enthalpy. So if I have a material that's coming in here and flowing out at some rate, the energy associated with stream, with this chemical, would be the enthalpy of the stream. So we can define an enthalpy of the material going in, we can define the enthalpy of the material going out, and that's because when we're dealing with flowing systems, we have to deal with enthalpy. When we're dealing with systems that are not moving, we only deal with internal energy. And again, PV is essentially more or less the energy it takes to make this fluid move. So if we know what the pressure and the volume of this fluid is, and we know what the internal energy is, we can calculate its enthalpy based on that formula there. Finally, I want to mention an important fact, and that is that these energy, internal energy, and enthalpy are state functions. What I mean by state function is they only depend on the state of the system. So for instance, if I define the temperature and pressure, let's just say 300 Kelvin, 2 bar, then the internal energy and the enthalpy of that system will be fixed at some value. It doesn't depend how I got there. It doesn't matter if I was at 400 Kelvin and then I cooled down to 300 Kelvin, or it doesn't matter if I was at 200 Kelvin and I heated up to 300 Kelvin. How I got here, it doesn't matter. These are state functions, meaning that once I know the state of this material, either its temperature or its temperature and pressure, for instance, then I know what its internal energy is and enthalpy is. And we'll talk more about how we can actually get those internal energies and enthalpies in a future discussion. So here's a quiz or a little question. If I have a system at state 1, so I'm here at state 1, and I want to go to state 2, so this is pressure on the y-axis, volume on the x-axis, I can go 3 different ways here according to this graph. I can go A, B, or C. And the question is, which one has the largest change in internal energy? And if you think back to the state function, the concept of the state function, well, it doesn't matter if I go A, B, or C, as long as I go from 1 to 2. It doesn't matter how I get there. The change in internal energy will always be the same no matter what path I take, as long as I have the same starting point and the same end point. And that's a big important concept in dealing with internal energy or enthalpy. As long as we know where we start and where we end, we can calculate the changes in internal energy and in changes in enthalpy, because it doesn't matter how we get there from one state to the other. So final concept I want to end up here is the idea of temperature. When we are dealing with thermodynamic quantities, when we are dealing with thermodynamic calculations, we need to work in an absolute scale. And in doing so, we work with either Kelvin or Rankine. So oftentimes we will probably most of the time work with Kelvin, but we may occasionally work with Rankine. But when we're dealing with changes in energy from one state to other, we have to make sure that we are working in Kelvin, otherwise we will make mistakes. So whenever you have a thermodynamic problem and you're given a temperature, if it's Celsius or Fahrenheit, you need to immediately convert these over to Kelvin and Rankine so that you don't make any mistakes in your calculation, because if you use Celsius or Fahrenheit, you may indeed get the wrong answer because you used temperature scale that is not appropriate for these thermodynamic calculations.